The goal in the algorithmic game theory field is that one of studying strategic interaction situations, modeled by using game theory tools and then searching for solutions to these models by using instead the theory of algorithms. Thus, algorithmic game theory is just a combination of game theory together with algorithmic theory. Simple examples of application are poker games. In 2017, the Libretto software developed by Carnegie Mellon University won about $1,800,000 US against the top 4 international poker players. Another example is security games, used in many infrastructures in USA, such as almost all the airports, ports, domestic flight, about 1,000 flights per day, protected using about 2,000 federal air marshals. In algorithmic game theory, a problem is customarily studied as follows. First, we start from a real problem and we provide a model of such strategic interaction situation. The model is called game mechanism. Then we need to define the space of strategies of the players. Second, we need to identify the most suitable solution concept for the situation we study. A solution concept defines the properties that the strategy of the player must satisfy in a solution. Different solution concepts may differ in terms of asymmetric information among the players, asymmetric communication, and so on. Third, the computational problem of finding a solution called equilibrium is studied. This is done by studying the computational complexity and then deriving an exact algorithm matching the complexity of the problem. In many situations, the problem may be hard, in the sense that it is unlikely that there is an efficient, polynomial time algorithm computing an exact equilibrium. So it may be interesting to study an approximation. In that case, it is necessary at first the definition of a solution concept that is approximate. And subsequently, we can study the problem of finding an approximate equilibrium, following the same line as before, that is, studying the computational complexity of finding an approximation and then deriving an algorithm matching the worst-case approximation guarantees. The structure of the lectures on algorithmic game theory is: initially, the game models are provided. In particular, all the representations used for strategic games are described. At first, the extensive form representation, subsequently the normal form 1, then the Hagen form, and finally the sequence form. Each representation provides a different description of the games and can be useful in different contexts. However, all these representations are strictly related to each other, and these relationships are discussed. Subsequently, the computation of the max-min, min-max strategies is presented. Then the Nash equilibrium is analyzed both in terms of computational complexity and in terms of algorithm. The last solution concept discussed in the lectures is the Stackelberg equilibrium. Finally, the last topic on algorithmic game theory is a special class of games called congestion games.